Hello everyone. In this session, we are going to discuss one sample example. I have taken one scenario for a context-free grammar, and for the same context-free grammar, I'm going to construct a Turing machine too. So whenever it is a context-free grammar, we are able to construct a push-down automata and a Turing machine. Like the example that we have discussed in the previous session, like when you are taking one example for a regular language, you are able to construct a finite automata, a push-down automata, and Turing machine, right? So when it is in context-free grammar, for context-free grammar, we are not able to construct a a finite automata. NFA or DFA cannot be constructed, but we can construct a push-down automata, and the same problem can be solved by this Turing machine too. So the language accepted by Turing machine is called unrestricted language. So whenever the problem is solvable, then we can construct a Turing machine for it. Okay. So with this scenario, we're going to start. Here, the scenario is actually Pranav has to travel back to his home every day from college. He used two paths. There are two paths, path A and path B. And each month, if he take path A once, he need to take path B twice. Okay, so when A is taken for n number of times, B has to be taken 2n number of times. And each given duration, he needs to take A path first for n number of days and sequentially followed by taking up the path as per the given condition. So the problem is nothing but it is A power n, B power 2n condition. So when he takes a path A for one day, like in a month it goes on for first n number of days if he is taking up A path, and sequentially it is followed by B power 2n condition, 2 power 2n number of times he is taking up this path B. Okay, so this is the question. So for this language, we are going to construct a push-down automata and we are going to construct a Turing machine too. So first we'll construct push-down automata. So my thing is like when you are coming to this video, it is preferable to look into the working mechanism of how does a basically push-down automata works and how does a Turing machine works. Just refer these two videos and then you can start coming here. Okay, a push-down automata is a mathematical model that accepts any language using stack as a memory unit. So here you have an additional memory unit that is stack, and using stack, we are able to solve a problem. Okay, so that is how a push-down automata works. And each step of transition, it is going to take one input symbol and one element from the stack will be popped out. And based on that combination, present state, the transition here is defined as the current state, current input symbol, and current stack symbol. It is going to make a transition to new state by pushing some element into stack. So this is how your transition actually looks like for a push-down automata. Okay, so now we are going to take the scenario. For this scenario, if you want to construct a push-down automata, like if there is a single A, it has to match with two Bs. Another A, another 2B, another A, another 2B. And we have stack as a memory unit. One thing that can be done is we can first push this Z node, like always. Remember to push this bottom element of stack to be there in the stack always. Z node will be there. And for each A, we have two pairs of Bs to be matched. So one thing that you can do it here is for a single A, whenever a transition scans a single A, push two A's into the stack. And for the next A, push another two A's. And for the next A, push another two A's. Okay, so the number of A's in the stack will be matching with the number of B's. Okay, since for each single A, we have put two B's into the stack. Okay, so now whenever B comes, we can start cancellation 1A, 1B. For all the B's, if there is a matching A present in the stack, then the input is accepted. So at the end of your input, if stack consists of Z0 alone, the input will be accepted. Okay, so this is the logic that you're going to follow. For this logic, I'm going to construct a transition diagram for this push-down automata. So first we'll start with the starting state. So I'm just going to have the state Q0 as the starting state. And in Q0, I'm going to have this Q0 for putting all A's into stack. Okay, as per the condition that we have discussed, first step is without consuming any of the input symbol, if stack consists of nothing, push this Z0 into stack. And when you're scanning, so listen to the working of the stack properly. So first step, the Z0 will be pushed into stack. And the next step, the Z0 that is there in the bottom element of stack will be removed and it will be taken out. Okay, so each step of transition, one input will be taken out of stack. That is a mandatory condition. We cannot do anything. Okay, so this A will be removed and the transition will work. Okay, and how does the transition will work? The input A is taken and stack consists of Z naught. So this Z naught that is taken out of stack has to be replaced back. And for the single A, you have to push two A's into stack. Right? How come you write the transition for it? For the single A, two A's has to be pushed on and the Z naught has to be replaced back into stack. So this is how you write the transition for it. Okay, so this is the first step of transition. And the second step on when the input that you're going to scan is A and the topmost element of stack will be taken as A. So for the next A in the input, this topmost element of stack will be popped out. This A that is there in the stack will be popped out. This input will be removed. Okay, so when the input is AA, the transition is this A that is popped out has to be replaced back. So 1A will be popped, 1A that is popped out is replaced back. And for this A, you have to push two more A's into stack. Okay, so totally three A's we are going to push into stack. One element that is popped out and two more A's for this corresponding one. Okay, so what happened here? For each A, we have pushed two A's into stack. Now the next step is when the input that we are scanning is like this is in a loop. So for how many ever A's we have in the next sequential pattern, two number of A's will be pushed into stack. And for the next step is when the input consists of B. So when the input consists of B, we are going for this cancellation phase. And in the cancellation phase, what you're going to do, this input B will be removed. One input will be removed and one A that is there in the top of the stack will be removed. So for this B, this A will be cancelled. When the input consists of B and stack consists of A, for this B, this A will be cancelled. So we are not going to push anything into stack. Okay, so I'm going to put this into a looping condition for all the B's in your input. You're going to pop out one A out of stack each time. So for this B, this A will be cancelled. For this B, this A will be cancelled. And for this B, this A will be cancelled. So while coming to the end, at the end of your input, your stack will consist of Z naught alone. So in that case, you can go for an acceptance criteria. Okay, so this is your accepting state. Now for this, so this is a complete diagram here. So whenever the language condition is given like this, the only thing that you want to know is like the number of A's that you're going to push into stack and the way to use a stack and find a solution for those kind of problems. Okay, so let me take one example like this one and I'll show you how this instantaneous description works. Starting from Q naught state, input consists of epsilon. First step is to put this Z naught into stack. Now Q naught, when the input is A and stack consists of Z naught, for this A in the input will be removed. And for one A, you're going to push two A's into stack. And next step is Q naught, when the input is A, for this A, you're going to put two more A's into stack. Already we have two more A's. Okay, so the Q naught, when the input is B and stack consists of A, we are going to the state as Q1. For this B, this A will be cancelled. You will be having three B's in the remaining step and three A's over here. Okay, so now again in Q1, it is in a looping structure. For all the B's in your input, you are going to cancel one A. So you have BB and AA in this. One B and one A is cancelled and it is put up in a loop. And for the next step of transition in Q1, for this B, this A will be cancelled. You'll have one single B and A is not into stack. In Q1, for this B, this A will be cancelled. So all the inputs are processed. So you don't have any other input to be processed. So it is epsilon and stack consists of Z naught. Okay. So in this case, you have a transition here either on epsilon as the input and Z naught as the bottom element of stack. You're going to pop out that Z naught too and making a transition to Q2 state. It is epsilon epsilon transition. So the acceptance is defined here as at the end of input, your stack is empty. So this is an acceptance criteria. Or other case, if you want to show at the end of your input, your transition is in final state. So both the ways the input is accepted. Okay, so this is how we construct a push down automator for the given scenario. So it is A power n, B power 2n condition. Twice the number of times path B is taken as the number of time of A. Okay, so now for the same example, if you want to construct a Turing machine. Okay, the taken language is a context-free language. So whenever the language that is taken is in regular language or a context free or a context sensitive language, you are able to construct a Turing machine. So any problem that is solvable, we can construct a Turing machine for it. Okay, so we'll see how to construct a Turing machine for the same scenario. So here you'll be like the Turing machine works like you have an infinite tape as a memory unit, and the input is written in the tape whenever we start the transition. We'll be having this BBB, and the Turing machine, the tape is splitted into cells, and each cell is capable of storing one input at a time. And we have a read-write head that focuses on the starting state with the first element of your input. So this is the default setting whenever a Turing machine is started. When you start a Turing machine, your input is littered in the tape from left to right, and each cell is capable of storing one alphabet at a time, and the transition starts from the starting state, focusing on the first element. The read-write head focuses on the first element. So this is a default scenario whenever a Turing machine is started. And the transition, each step of transition is based on the current state and the current symbol on the tape. You're going to make a transition to another state by making some replacement into the tape symbol and moving left or right. So each time this read-write head is capable of moving left side or right side, and the element in the tape can be replaced to other symbol, or if you want, you can have it in the same symbol too. Okay, so logically, I'm just going to say what is my scenario I'm going to work on. So first step is I'm just going to take this A, cancel this A as X, and I travel right until I find a B. So whenever I find a B, I'm canceling it as Y. Okay, so for a single A, I'm going to cancel two Ys. Come back, take the next A, cancel next two Bs. So at the time of coming back, when I want to take the next A, I don't have a A here. If it is Y, if all the remaining tape is Y, I'm going to have the accepting criteria. Okay, so this is the logic that I'm going to follow here. Now construct a Turing machine for it. So I'll be having the state as Q0. In Q0 state, when my input is A, this A will be cancelled to X and move right to the new state as Q1. Okay, so this A will be cancelled to X. So one A is cancelled. For that A, we are going to find a pair for it. Okay, the problem is A power n, B power 2n. So for a single A, I'll be having two B's. So here, while traveling right side, I may have n number of A's. That doesn't matter. I keep on moving right until I find a B. So when I find a B, I'm going to cancel this B to Y, move right to Q2 state. For a single A, I'll be having two B's. Okay, so I'm going to check the next element also. If that is also B, cancel that into Y, move right. So this is one sequential cancellation. For one A, two B's will be cancelled. Okay, so after cancellation, what we are going to do? So one A and these two B's are cancelled to YY. Okay, so after cancellation, what I have to do? I have to come back. It is the left side move. After cancelling your second B, we need to come back and take the next input. So while coming back, I have to take the next A, right? So while coming back, I can have any number of Y's or any number of A's. I just keep on moving until I find the X. Okay, see here, I have the transition like this. A, Y, Y, B, B, B. So while coming back, after cancelling this Y, while coming back, I can have a Y or A, it doesn't matter. I come till this X. Since X is the last cancelled A, so the next element is the one that you want to take it up. So I will be coming left until I find the X. So once after finding X, what I'm going to do? If there is an X in the tape, the X will remain as it is, and I'm just going to move one step ahead for taking the next input. And after taking next input, what I'm going to do? I'm going to repeat the same process. For this X, I'm going to cancel it as, for this A, I'm going to cancel it as X. And moving to Q1 state, in Q1, for any Y, it doesn't matter. I keep on moving right until I find a B. Okay, so this will be cancelled as X. I'll be coming as any Y's here. It doesn't matter. And once I find a B, in Q1, when the input is found as B, cancel that B to Y and move one step ahead to Q2 state. In Q2, if my input is another B, cancel that B also to Y and come back. Okay, so after cancellation, we are going to this Q3 state while coming back. So When we are coming back, we can have any number of y's. It doesn't matter. We have to come until you have a x. So Q3 in x, what does that means? Q3 in x, it means that this is a cancel, last cancelled A. So while taking the next input, you have Y. So while taking the next input in Q0, Q3, when the input is X, it goes to Q0 state. And when the input is Y, it actually means that all the A's are cancelled. Okay, so when all the A's are cancelled, when you have Y here, so Y will remain as it is. We are going to verify whether the remaining elements are also cancelled. Okay, so it is like a verification phase. If you have a Y, all the remaining elements should be Y until we find the blank symbol, then we are going to accept it. It means that we have A power n, B power 2n condition. So here we are going for this Q4 state. In Q4, we can make a self-loop condition, right? For all your Y's, Y will remain as it is. We are moving right. And once we find a blank symbol here, you're going for this acceptance criteria. Okay, it means that we have n number of A's followed by 2n number of B's. Okay, so this actually works when the input is pakka. When you have a proper input of the given acceptance criteria, your input will be accepted. And we have a special rejection state too. So when you are defining a rejection state, either your number of A's will be higher or the number of B's will be higher. So when the number of A's are more, you will be cancelling one A here, but that doesn't have a pair here. In Q1, if you don't have any B and have a blank symbol, in Q2, if you have a blank symbol, so those things are like you don't have any extra B. See, when you have a 3 A's and 2 B's, so for this A, these two will be cancelled. And for this A, when you are searching for, you don't have a B. Instead, you will travel till blank and you don't find it. Okay, so in Q1 or Q2, if you have a blank symbol, it is fine. It is like you don't have any B's for cancellation, proper B's for cancellation. Okay, so this is one scenario. Another scenario is when you have an excess of B. For single A, when you have 3 B's, for this A, these will be cancelled. While coming back, you don't have anything, you'll have the cancelled B alone. But while checking up the remaining status here, all the inputs should be processed, right? In case if you have an extra B in this place, then it is rejected. So in Q4, when you have an Y, so all these criteria are there for Q reject category. Okay, so I'll show you one sample example of your acceptance and rejection category. Okay, sometimes in your question paper, they will ask you to take one input for acceptance and take one input for rejection. So I can take the same input for acceptance criteria starting from Q0 state. In Q0, when the input is A will be cancelled to X and we are moving right to Q1 state. In Q1, for any number of A's, we stay in Q1 itself. And Q1, when you find a B, this B will be cancelled to Y, move right to Q2 state. In Q2, if the input is B, cancel that also to Y and move left. So this, after this, your transition will look like this to Q3 state. In Q3, either the input is Y or A, we keep on moving left until we find the X. And in Q3, when you find the X, you're going to make one right side move to Q0 state. Okay, so you'll have it XX, YY, BBY. Sorry, BB, it is blank symbol. Okay, so now coming to this place in Q0 state, what it do? In Q0, this A will be converted to X and we are making a transition to Q1 state. In Q1, if you have any Y's or A's, we keep on moving right until we find a B. In Q1, when the input is B, B will be converted to Y. Make a transition to next step to Q2 state. In Q2, if the input is B, cancel it to Y. So your input is XX, YY, YY, blank symbol. After cancellation, you come to this Q3 state. In Q3, whether it is Y or A, we keep on moving left until we find the X here. So in Q0, when the input is, sorry, it goes to Q0 state. Q3, when the input is X, it goes to Q0 state. It is XX, 1, 2, 3, 4. So Q0, when the input is Y, what it do? Q0, when the input is Y, it goes to Q4. Okay, move right to Q4 state. In Q4, we are going to verify whether all the inputs, remaining inputs are Y until we reach a blank symbol. If you have extra B, that will be rejected. Okay, until it reach a blank symbol. If it is all Y, we keep on moving. And in case if it have a B here, then it will be rejected. Extra B input will be rejected. Okay, so Q4, when it is a blank symbol, we are going for this acceptance case. Got it? So this is one input for acceptance criteria. And I'll show you one example for your rejection. I'll take a simple example. When the input consists of a single A and B and a blank symbol. So it starts from Q0 state. Q0, when the input is A will be cancelled to X, and you are making a transition to Q1 state. In Q1, when the input is B will be cancelled to Y, and we are making a transition to Q2 state. So in Q2, if it is blank symbol, we are going for an rejection state. Blank, it will be Q reject. Okay. And how will you write an instantaneous description for it? So the logically, I think the working mechanism could be clear for it. How to construct a push-down automator and how to construct a Turing machine for it. Okay, so the next step is how to write, and this is a tape structure, right? This is how a tape will look like each step, and how you're going to write an instantaneous description for it. So instantaneous description is writing it like the extra exact tape structure could be written as it is A, B, B, and wherever your read-write head focus on, you have to write the state in the prefix of it. So Q0 has to be written here. Okay, so this is for the first step. And the next step is B is the state, and here you have to include this. This is the place where you have a read-write head. So this is converted into XQ1BB. Okay, from this, we are moving to the state. And the next for this step, instantaneous description is XY, and here you have the read-write head. So you have to insert your state here. From this, we are going to XY Q2B, and after this, the last step is Q rejection. It is XYB Q reject. Okay, so this is called a single move in a Turing machine. From this state, you are moving to the state. From this state, you are moving to this place. Okay, so this is called instantaneous description, ID description. And when you want to write it as a whole from Q0, when the input is ABB, we are going for this Q rejection state. On multiple transition, we received this, right? You can write it as XYB Q reject. The input is rejected at this place. Okay, so this is called on multiple moves. When it is closure, when it is an asterisk symbol, it is clean closure step. On 0 or more move from this state, we are reaching this state. So this is called an on multiple moves transition. Okay, so whenever a scenario is given, we have to try to find its corresponding language description. And once the language description is known, it will be easy for us to convert it. Okay, thank you.